So, uh, so do all of you know about pigeonhole principle? Like,
Yeah, I know.
okay. So the some exposure you've had with it before.
Yeah, like when my children solve and they say, so the idea, I know, like there's one extra and it fits. Like I
Huh.
have never done anything myself, but
Okay. Okay. So I guess we'll just start by establishing the statement of it. Yeah. So if we have the statement, the way it is usually narrated is quite simple only. So if we have n boxes and some m pigeons, so where we want to keep pigeons inside the boxes, and we have more pigeons than there are boxes. So there will be at least one box which has more than one pigeons, right? So I think like the statement is quite clear this way. But we'll try maybe one or two problems, try to solve one or two problems using this. So one of the common things that comes up is, I think, the handshake problem. So say if there are seven people in a room, then at least say two of them will have same number of, and like they're shaking hands with each other. At least two of them will have the same number of handshakes. So this is the statement. Maybe I'll write it. Hmm.
So different handshakes. I mean, there can be a person who is not shaking hand with anyone. So zero, then with one person, two person.
So we are talking about one person here.
Suppose means zero, a person who shakes hand with zero people,
Yes.
then with one person, then with two person, something. So maximum it can be six.
4, 5, 6. Yes. Yeah. A person
But
can't.
if there is,
Yeah.
yeah, but zero and six cannot exist together.
Mm. Hmm. So we need to like say what we mean by these numbers. Maybe like can we uh, define a little more
Um,
what we mean by these numbers?
Means you
Or
mean the boxes?
range of handshakes possible from minimum to maximum,
yes.
right? Either you can have one. These are the range of possible handshakes.
Yes. So number of possible.
Number of handshakes, number of
Huh. Handshakes one person does or in the room. So I think this is one person.
So if there is one person or any person who is not shaking hand with anyone else, then
Yes.
there can't exist a person with six shake hands.
Yes. Yes. Yes.
Okay, so out of zero and six, only one can exist. Means one possibility,
So it's either these
or
or
these. So there are how many possibilities? In all, six possibilities.
hmm, for one person. Yes.
And there are seven persons we are talking about.
Yeah.
So then that means what? At least two of them are doing the same number of handshakes.
Hmm. Right. I think that okay. So if does this make sense to everybody?
Yeah.
Right? Okay.
In
yeah.
terms of boxes and pigeons, we can say we can call these as 0 to 5 as number of boxes. Means there are six boxes
Hmm.
and seven pigeons. So I
Yeah.
mean that
So
way we
pigeon.
can yeah.
Yeah, maybe yeah, like I think that'll be good. So I'll just say pigeons will be the people here
Ah,
who are shaking
yes.
hands. And yeah, the boxes are mm, yeah, what are the boxes here? So
Number of possibilities.
yes, number of possible handshakes. Yes. All right.
Number of possible handshakes per person.
Yes, per person.
Per person. Yes.
Yes. So, yeah. So, one sort of like if I make a picture of this, I mean, when we try to say make a picture of this, say 7 people, yeah, it could be like one person could have a handshake with this or this or this or this or this, and we can basically map so 1, 2, 3, 4, 5,
One
6,
more.
one more, yeah, sorry, yeah. So we can basically make a map of all the handshakes that are happening here, right? So like I'll not go too much into this, but if this is something you're curious about, this kind of also emulates a graph. And like a simple graph, so multiple edges not allowed and loops not allowed, but a simple graph. So this also kind of gives you a theorem on it. So how does it translate? At least, say if we are making a graph, at least there will be at least 2 vertices which will have same number of edges. Did I get that right?
Yeah. There'll be at least 2 vertices with the same degree.
Yeah, same degree, right?
Same
Means
degree.
they are joining.
Hmm.
For example, the vertex 1 has 5 degrees 5, whereas 6, 5, 4, 3, 2 has degree 1.
Yes, 6, 5, 4, 3. Yes.
Yeah, and 7 has 0. So
Yeah.
there will exist at least 2 vertices with the same degree.
Yeah. Yes. Maybe we'll take another example. When we look at fractions, for example, say 1/2, 1/2 has a terminating decimal expansion. But let us look at fractions which have non-terminating decimal expansions for now. So, yeah, how do we know that basically all rational numbers have a non-terminating repeating decimal expansion? Basically, there will be repetition that happens at some point in time, right? So any rational number, basically any number which can be written in the form of p by q will have a repeating decimal expansion.
It'll be either terminal or it will be a recurring non-terminal.
Terminal or recurring now, yeah. Yes. So even if it is terminal, we can consider like 0, 0, 0 as a recurring. Just to
Oh.
keep the
Okay,
statement
okay. Got it.
small, yeah.
When you divide by q, there are only a given set of reminders that are possible.
What does that mean, Preeti?
Like, I mean, like if you divide by 7, the reminders possible is only from 1 to 6.
0
Right.
to
So to
0 to 6.
At some point, it's going to repeat.
That's it, finished. At some point, it's going to repeat.
I mean,
No, but remainders are fine. Like, how does having a fixed number of remainders guarantee that there's a repetition? A repetition will happen.
same reminders means you are dividing the same number again and again, right? So it's going to give you the same set of answers.
Can you make it a bit more sort of the logic a bit more? I think we need to make the logic a bit more solid. I get where you're going, but some more, how do we phrase it?
Like you will get only the reminders have to repeat because there is only a set number of reminders.
Yeah.
So eventually you will repeat the reminders, and there are like the slots are n number of slots, right? I mean, they are infinite, but the number of reminders you have, they are limited. So
Yeah.
at one point you are bound to go back to the same reminder.
Yeah.
But like I don't know how else to.
Then what happens in 22 by 7?
Yeah. Do you want to try?
Okay, so
I
5.
tried 22, but there also you reach after 3.14285.
Okay, so 7 threes are
21.
21.
1. 7 ones are
Then 4.
3.
yeah, 7 fours are then 2, then
Once you reach 50, it will recur.
1 4 2. I
Hmm.
hope I'm doing the multiplication correct.
Yes, correct, correct. 14, 60,
Um,
56.
8 the 56.
yeah, then 4
40,
4.
yeah,
40.
35.
so 5s are
5.
So once you have 5,
5 0.
it's
So
just
now,
like
7s are 49.
yeah.
So 1.
it's the same thing you get when you divide 12 by 7. Now the remainder is 5. The
1 4 2 and 5. What was the
7. 7. 7s are 49.
7,
and then 1 has come
1,
back again.
So 10. So 10.
yeah,
Okay.
1, 4, 2, 8, 5. 7, 1, 4, 2, 8, 5.
Yeah.
Then
So
it repeat.
yes.
1 4 2 8 5 7 repeat.
So yeah, so it will come back. So we'll just organize. I think everybody has got an idea of how to do it. I think we'll just organize our thoughts. So we already know that P by Q has a repeating decimal expansion, right? It's an infinitely repeating decimal expansion. So we know there will be like infinitely many times I have to do this. I have to, right? That is already there in our assumption. So, but like you all said, the number of possible remainders is fixed. And in fact, here it is 0, 1, 2, 3, 4, 5, 6. Only 7 possibilities for remainders are there, right? So I need to sort of keep repeating this process infinitely many times. So like you said, it has bound to repeat. Or if I need to use the pigeonhole terminology, how does it go? So what are the pigeons here and what are the boxes here?
Boxes are the remainders. If 0, 1, 2.
Yeah.
You divide by, let us say, by n, then 0 to n minus 1 are our boxes.
Huh. So here there are 7, 0 to 6. Yeah. So 7 boxes are there here.
7 boxes, yes.
Yes. And what are the pigeons here?
It's number of digits after the decimal point.
Yes, yes. Can you elaborate, Gauri, why is it number of digits? Can we just verbalize?
So we are as we are dividing, we are
Hmm.
getting we are getting more and more accurate value of the quotient, right?
Hmm.
So each time we this thing of getting down a 0,
Yes.
that is basically adding one digit after the decimal point.
Hmm.
So yeah, least significant digit after the decimal point. So there are infinitely many of them.
Yes.
So those are the pigeons.
Yeah. So every time we are doing this process, it corresponds to 1 digit here. And so we have to do this infinitely many times. So either, yeah, I can say like each of the step, whatever that bringing down thing is, or we can just, because there's a 1-to-1 correspondence, we can just say, pigeons are the digits basically. Digits, should I say digits or should I say places?
Yeah, I don't know. Digits.
Yeah, it's just
Digits.
okay. It's the same. I don't know the formal terminology, sadly. So digits after the decimal point,
Yeah.
and there are infinite many of them. So which is definitely greater than 7.
Right.
So remainders will repeat, which means that yeah, as soon as I get a repeated remainder, I will get a recurring decimal. what is also like interesting is, so can we make any comment about when the recurring will start based on this? When the repetition will start happening? Like here it started after 6 places. Can we say anything about, or can we say this about every fraction, for example?
You can say maximum.
I don't think.
The length of the repeating unit can be at most n minus 1 if we are dividing by n.
Yes. Yeah. Why n? Why not n? Why n minus 1?
If it is 0, if the remainder comes as 0, it terminates.
All right. Oh, so yeah, it's actually just 1, 2, 3, 4. Okay. Yeah. Good point.
So there are only n minus 1 possible remainders.
But we cannot predict when it's going to repeat.
We cannot
We can
predict.
say that it can go till n minus 1 maximum.
Yes. And the length of the cycle is n minus 1.
Yes.
I doubt if we can say where the cycle starts.
Yeah, we don't know. We cannot predict where the cycle is going to start. That's
Yes. So in a more fractional part will be cyclic. After one cycle it repeats. Here after one cycle it is repeating. But I think this also points us to one of the limitations of pigeonhole principle, which is key. So when I have say boxes and when I have pigeons, it doesn't. One thing is like it doesn't tell me which box will have more than one pigeons.
more than one pigeon.
Yeah, and which means which number will here in this case it means which number will come twice. Pigeonhole principle itself does not tell me anything about that. But does that help us? Yesterday I was sure that we can predict, but today I'm not so sure.
Can't predict where it starts.
Where it starts.
If it's 1 by p, a prime number, then the rep unit starts right after the decimal point is something that's randomly coming to my mind, but I am not yet recalling the justification. 7, I think, is thoda special that way.
What would say 15 by 7 if I do? I get 7 twos are, and what? Yeah, 1 will be left.
And it is the same as 1 by 7. So 1, 4, 2, 8, 5, 7.
So won't it happen for 7, 8, and 9 also, I guess then?
But if we divide 18 divided by 7, we'll get something else.
Oh, is it?
18 divided by 7.
18 twos are 14. 4. Yeah, 7. Oh, okay, 7 fives are because it overshoots the 7 fours are 28. Even if it was 30 here, it wouldn't have happened, I guess. So maybe 17 divided by 7 will be,
So 14.
yeah, and here it will be like 4. So
Again,
it's 3 here.
24, yeah, 28. So
But
it's not matching.
But in this case, if you continue, 7 divides 18, it'll continue as 5, 2, 1, 4, 2, 8.
5, 2, oh, here?
Yeah.
5,
Write
2,
it there.
1,
2,
4.
1, 4, 2, 8.
Oh, 1, 4, 2, 8 is coming here also. 1, 4,
It's
2,
the
8,
same,
5.
like the same numbers, like rotated around.
Ah.
And here it will become 4, 2, 8, 5, 7, 1. 1,
Yeah,
4, 2,
once
8,
you
5,
have that
7.
remainder, that recurring pattern is the same because it's the same multiple quotient. Be the
Sorry,
same.
here it is
Gauri,
5,
you will
7.
get 5, 7. How
5,
will you
7.
get 2?
Not 2. My bad. 5, 7.
7.
My handwriting when I wrote it down was so bad, I read my 7 as a 2. 571428.
Yeah. Yeah, I was just thinking about where the 7 has gone now, but okay. And then this is the repeating. So even the repeating cycle is same. I mean, it's
This
like
might be a speciality of 7.
oh, acha. That also relates to the divisibility rule we have for it, is it? No. No, I don't know. I don't know.
Sure.
Oh, should we try it with 9? Wait, 21 divided by 9 will be what? 3. Okay, this will go for a long. Yeah, 2.33. Okay, interesting. Now I have no idea about how this works, but it's an interesting thing to explore in itself. Yeah.
Suddenly, we've taken a number theory turn in the session.
I am, yeah, happy to. So again, I am like okay with exploring this or going forward, whatever, like what.
Yeah, we can explore the reminders. I mean, if there is another PHP session where we are exploring more, then we can continue. Or if this is the only session, we can do maybe a different problem.
We can meet again for the thing. Yeah.
It'll be interesting if we can predict when the recurrence will start, right? But I think that is
So I was feeling until yesterday that that also should be less than n, but I doesn't convince me anymore today. Yeah. So the reason I was feeling it'll be less than n is so the repetition will start when the same number appears, right? So the question is how many steps would it take for a same number to appear? And if there are 1, 2, 3, 4, 5. So I have to make sure I continue for a long time without
Getting any of
getting the same remainder.
Hmm.
But that doesn't seem possible because I only have 6 options here or 1, 2, 3, 4,
Right,
6
right.
options here.
Right.
Which is why I felt it should be less than n.
Yeah, that makes sense, no?
Yeah, but I feel like there must be counterexamples to this where like it starts after a million digits. I don't know.
How is it possible? It cannot. क्या million digits आएंगे? Because one repeating digit means cycle. That
Yeah.
is,
Yes.
and there are limited number of reminders possible. Okay, wait. Uh, what about like 143 or something like that?
Oh, so take example of 22 by 14. 11 by 7 shall I take?
7 में तो ऐसे ही आता रहेगा.
हाँ.
So we can take something else.
Oh, 22 by 21. Oh, 22 by 21. Did they write any number? Gives same 6 digits. 21 fours are 84. 16.
0.047619 Hemant has.
Oh, okay. 1, 0, 4, 7, 6.
7619.
What happens after 9?
Oh,
047619. Repeats. Okay.
oh, 047619 repeats.
Okay.
Repeats from 0. So, yeah.
Yeah, this right? 047619.
How about 22 by 14? What happens? 1.571428. 57143. 571428.
How did you do it so fast?
Calculator.
Oh.
What about, let's try 30 by 22. Yeah, we can't find one example where the recurring part is starting after some few digits. चीची क्या हो रहा है?
Yeah, yeah, again, I'm feeling that it's not possible. But I also am getting a feeling this is a very suspicious thing. I don't know to believe it.
2 divided by 30.
2 divided by 30.
I mean, obviously, this will now start.
3 hai na, so there is.
Yeah. 3 hai, but because 10 hai, so it will start, the recurring will start from the 100th place, 0.066666.
Yeah. It's still less than 30, no?
Still less than 30. Yes, of course.
Yeah, I don't think it should be possible to get.
So definitely it has to be, I mean, the place where the recurrence starts definitely has to be less than the divisor.
Why?
The same reason that you gave. I mean, there's no
But
way.
my second thought, I'll just share the what was. So if I want to not have the same digit here, basically, I want to avoid having the same digit here. But the thing is, like, so if I have 30, so 100 will also give me 9 5s are 95, 101, 19 5s are 101 will also give me 5s are 102. Like, basically, any numbers. Like,
So it depends on the number of digits in numerator and number of digits in denominator. So it can change only when what you are taking down in division is not a 0, right? If you get the same remainder and still end up getting a different quotient, that can only happen if what you're bringing down is not, I mean, is a different number in this division process. So that can only happen until the significant digits of the numerator are used up. And we've started pulling down zeros. Once we start pulling down zeros, it's the same. So that is when getting the same remainder will ensure the same digit in the quotient.
Yeah, basically we can't avoid, only till n number of steps I can avoid having the same remainder, right? That works. I hope there's no.
Yeah, I don't see any. So it's going to be much smaller than that actually. I mean, practically we are seeing it being much smaller than.
Yeah. But yeah, there will be cases where we can get 18. Oh, that can be constructed, in fact. We can construct numbers whose repetition starts from 18th by trying to choose different remainders and like maybe going back the process. I don't know. Or a simple, okay. So basically, I try to reverse engineer. But yeah, I mean, it says repetition cycles.
What is I forgot. Okay, the conversion from recurring decimal to fraction. How do you do that? There's something that, right?
Yeah, we take it as equal. We'll try with 0.9. I think that will remind us. It's 0.9. Oh, so assume this is.
Oh, that is 1.
Yeah, this is 1, but the way we do it is
right.
equate it to P by Q, and then
You just multiply it by 10 and then subtract. And
10x is equal to also 0.
oh, sorry, X. Yeah. X, not.
Okay. So 9x is equal to 9. So x is equal to 1. Okay. So 0.42 bar will be.
Yeah. The only loophole is we don't know if we know the addition of infinite digits. Kind of.
That way we are assuming.
Subtraction here, but yeah.
That's right. Oh, so then to, I mean, the fact that we can write a decimal like what you wrote will lead to a ratio.
Yeah.
0.157424242.
Yes.
Because we can write this decimal, we can write a ratio, I mean a fraction which will generate this.
Yeah, we can write a fraction which will generate this, but then it will be like, we only know the cycle is of 2 digits, which means it can practically be any denominator. We only can say that the denominator is greater than 2 here.
I can't wrap my mind around that we can predict. Like there are so many possibilities. If the reminder that you need can occur for a variety of combinations. So I don't know.
Yeah, it feels. Yeah, maybe we'll get some time to think over it and then come back next week on it.
Yeah, we can think about it this week and see if we can make some progress.
Yeah.
Yeah, I think we can pick up next week.